And 7.2, going to be working more with hypothesis test, and just want to start the video by going through the steps for the hypothesis test again. Always identify your null and alternative. The null always has a statement of equality in it, and every problem is going to have a level of significance alpha. Typically that's around like 5%. And the point is, if the probability of our sample is less than alpha, then it's a very unlikely sample, and that's when we're going to reject the null. So here's kind of a visual of that. We'll get our sample back, and the p-value, or the probability value, is the probability of getting a sample like the one we did, or one that's even further away from the mean. So we'll get the probability of our sample being as far in the tail as it is, and then we always follow this decision rule. If the p-value is less than or equal to our level of significance, our alpha, that's when we reject our null. If it's not, we fail to reject our null. And so problem 1 here, it gives you a p-value, and it's just asking you to compare that to the level of significance. If it's less than it, you're going to reject your null. If it's not less than your level of significance, you'll fail to reject the null hypothesis. And 2 and 3 are the same. I'm just looking at 3 for an example. The rejection really depends upon your alpha, your level of significance. For example, a p-value right here, 0.0503. If alpha is 0.09, our p-value is less than that, so we're going to reject. But if we change alpha to 0.02, we would fail to reject because 0.05 is bigger than 0.02. And so why do we use different levels of alpha? It really depends upon what the consequences would be of a type 1 error. If a type 1 error would be really, really bad, you want a really, really small alpha, which would reduce your chances of getting a type 1 error. And why this works, the smaller you make your significance level, it means your sample has to be further and further out into the tail before you're going to reject the null in favor of the alternative. So remember, there always is the chance that your really unusual sample out in the tail is just an unusual sample. At the 5% significance level, 5% of the time, you're going to be making a type 1 error and rejecting the null. But at the 1% significance level, that's when you're even further out in the tail, only 1% of the samples fall that far away from the mean. So you would only make a type 1 error then 1% of the time. And so for problems 4, 5, and 6, we're actually going to find the p-value for the test statistic that we get back from our sample. So it'll already calculate what the z-value is of your test statistic, and we're just going to hop in Excel here, and you use this formula for a left tail test. For a right tail test, you want to do 1 minus that formula, and for a 2 tail test, you just want to double the value back that you get back from the formula. And so recall what that formula gives you back in Excel. It's the probability of being at that z-value or even further to the left. So left tail test, like I mentioned, just type it in directly. Right tail test, it would give you the probability of being to the left. So 1 minus gives you the probability of them being to the right of that z-value. And a 2 tail test, if we know how far out in the tail our test statistic is, we want to see the probability of being that far out in either tail. So whatever the probability is, we just double it, and by symmetry then we have the probability from both tails. So just to do one here, looking at number 4, the p-value for a left tail test, here's my z statistic, negative 1.69. So for left tail, negative 1.69, true. When I hit enter, then it gives me the probability of being that far in the tail or even further. So then based on alpha, whatever the alpha is, you would decide whether to reject or not. In this case, that is smaller than alpha, so I'm going to reject the null hypothesis. So number 7, we're looking at what's called a critical value now. So before we were finding the p-value for our specific sample, the probability of getting a sample like the one we did, the critical value is going to be all completely based on alpha. And what it does is it is the Markov line, the cutoff point for where there's that much probability of being in the tail. So a critical value for a left tail test, alpha 0.02, it's the cutoff line where there's only 0.02 of the distribution in the tail beyond that line. So how do you find these cutoff lines? We're again just going to use a formula in Excel, and it's norm.s.inverse. And then you just type in your alpha, and Excel gives you back what the cutoff line would be for that particular probability. So for 0.02, if you put a 0.02 in there, you get back our critical value of negative 2.05. Now by symmetry, if you want to do it a right tail test, use the same formula. Excel is going to give you a negative value back. Just multiply that by -1, or essentially you're going to be removing the negative sign, making it positive to get the critical value for right tail test. So looking at the same value, if I wanted 0.02 in my right hand tail, I use that same exact formula, and I would just know it's positive 2.05. Now for a two-tail test, if I wanted there to be 0.02 split between both tails, what you need to do is divide your alpha in half, because you want half of it to be in each tail. So you use the same formula and just make sure you divide your alpha in half. Split it between the tails. So it gives you the left-hand critical value back, and the right-hand one would just be the positive version of that. So that would be like this picture. Half of 0.02 is split between the two tails, and we know what those cutoff lines are from Excel here. And then so how this works now, if you would look at your sample and find the test statistic for your sample, if it's even further away from the mean than your critical values here, that's an alternative way to decide to reject the null hypothesis. And so there's really two ways to decide whether to reject the null hypothesis or not, and they're like two sides to the same coin. You're always going to reach the same conclusion no matter which method you use. One's the value. You find the probability from your test statistic, and if that probability is less than alpha, you decide to reject the null hypothesis. Or you just look at that test statistic, and if it's further away from the mean than the critical value, you again decide to reject the null hypothesis. And just look at what this means. If the test statistic is further away from the mean, then it has an even less probability of occurring than the critical value. And what's the critical value's probability of occurring? Alpha. That's how we get the critical value. And so if our test statistic is further away from the mean, it means the test statistic's probability is below or less than alpha. So it's two ways of saying the same thing, just two different ways to decide whether you reject the null hypothesis or not. And basically with the picture, just think if you're really far away from the mean, far in the tail, it's an unlikely sample, that's when we're going to reject the null hypothesis. And so that gets us up to number 10. And I'm going to go through this word problem here. A random sample of 82 8th graders scores on a national mathematics assessment test has a mean score of 272. So this test result prompts a state school administrator to declare that the mean score for the state's 8th graders on this exam is more than 270. So here we have a statement, a claim, that the scores are more than 270. So right away I know that has to be the alternative because it's not a statement of equality, and it's that our scores are greater than 270. And so then I know what my null is. It has to be the complement of that, which is that the mean is less than or equal to 270. And recall, this is the claim that we're making about our mean. And so using all the information in the problem now, we're going to find the test statistic for our sample, the p-value, and decide to either reject or fail to reject the null. So in Excel, make note of what the standard deviation is and what alpha is. This will help determine whether you reject or not. And then get the information from your particular sample. So the sample mean we were told was 272 and our sample size was 82. So central limit theorem tells us our sampling distribution, if our sampling distribution, we're going with the assumption that our null is true, so our sampling distribution is going to have the same mean as our population, and we know the standard deviation is going to be population standard deviation divided by the square root of the sample size. So that's how you get the mean and standard deviation for your sampling distribution. And now let's look at our particular sample, what our result was. So you take how far away your result is from the mean and divide by the standard deviation for your sampling distribution. And so that gives us that our sample was this far away from the mean, and the probability value of that, of being that far away, this is a right tail test, so I need to do 1 minus norm.s.distribution, and then my test statistic, my z-value, comma true. And so that's what I get, 0.2730. Since that value is bigger than alpha, I do not reject the null hypothesis. Basically what happened, we assume that the null hypothesis is true, so we get a normal distribution with 270 in the middle. Our sample came back right here. It had about 27% chance of having a distribution there or even further away. And we were only going to reject the null if we found that it was only 15% likely, so if it was even further into the tail. And so it's not far enough in the tail for us to reject. Looking at the critical value approach, you don't need it for this particular problem, but just to tie it all in, if you type in what your alpha is, 0.15, you get the critical value for your alpha. Now, right tail test, I know I'm just going to make that positive 1.03. So positive 1.03 is the cutoff mark, where only 15% of samples will fall past that. And our test statistic came back at 0.6. So it wasn't as far away as 1.03, it was only 0.6 away from the mean. So again, we don't have enough evidence to reject the null. Number 11 is going to be very similar to number 10, just with some different values for your sample and your population. And number 12 is going to be like the previous problems, but instead of using the p-value approach, it is actually going to want you to use the critical value approach to talk about whether you reject the null hypothesis or not. And number 13 and 14 are the same. If you have any questions about how to set them up, or any part of this video was unclear, please let me know. On every problem, make sure you're rounding to the correct number of decimals. Pay attention to that. Pay close attention to alpha. It will depend on whether you reject or not. If alpha is 0.05 or 15, or it's going to vary from problem to problem. So pay close attention. And yeah, let me know if you have any questions about hypothesis test.